Hi, we're going to go ahead and take a look at the section 9.3 notes. For this section, we are going to find confidence intervals to approximate population variances and standard deviations. More often than not, we'll be estimating standard deviations and not variances, but you could be asked both, so make sure you read every single word of the problem to know what you're being asked to find. So the first thing I want to say is that there is no calculator function for these. You will have to use formulas and a table of values, unfortunately. It's not quite as simple as the last two sections. So first of all, when you're asked to find the confidence interval, you'll need to find this alpha value, right? It's the complement of the level of confidence as a decimal. You'll notice in the formula you will need the sample size, and you'll need the sample variance, which is just the square of the sample standard deviation. And then you have to find these chi-square values in the denominator of the formulas. And those chi-square values are found in a table using n-1 degrees of freedom. As mentioned above in the notes, the shape of the chi-square distribution changes depending on the degrees of freedom, which is why you need to know the degrees of freedom to find the chi-square value from the table. The formulas down here are identical, except now you're seeing a square root. That's because the formulas above are for the variance, sigma squared. The formulas down here are for sigma, which is the standard deviation. The formulas just are changing by having a square root over them. So here's just a sketch of what this chi-square distribution looks like. You'll see that it's not symmetric, and that is why the confidence interval will have a slightly different structure. It will not be point estimate plus or minus margin of error. It really can't be, because the point estimate is not going to be in the center of this distribution. So this picture kind of tells us the main point of these two different chi-square values in the formulas. I put some steps here out in words, but we're going to go ahead and go over an example together. We'll need this table as well. So let's read through this. A simple random sample of size n is drawn from a population that is known to be normally distributed. The sample variance s squared is determined to be 19.8. So we have a couple of things here. We have the sample variance. Okay, so for part A, it says construct a 90% confidence interval for sigma squared if the sample size is 10. So here the sample size is 10, so the degrees of freedom will be 10 minus 1, which will be 9. So the degrees of freedom matter because you use that when you look at the table. Next, we need to figure out the subscripts for our chi-squared values. I just want to scroll back to the formulas really quick. You'll see that for the lower bound, the subscript is alpha over 2. And for the upper bound, the subscript is 1 minus alpha over 2. Well, those values aren't super difficult to find as long as you know the confidence level. So here the confidence level is 90%. That means that alpha is equal to 0.1. So remember that alpha, the alpha level is going to be the complement of the confidence level. The complement of 90% is 10%, but alpha is expressed as a decimal. So if alpha is 0.1, then alpha over 2 is 0.1 over 2, which is 0.05. So that will be the subscript for our lower bound chi-square value. And then 1 minus alpha over 2 will be 1 minus 0.05, and that will be 0.95. So we need to find two chi-square values, chi-square sub 0.05 and chi-square sub 0.95. This is just the Greek letter chi. It looks like a fancy X. I know it looks like chi, but it's pronounced chi. So both of these values will be found from the table using 9 degrees of freedom. So let's scroll back up to our table and see if we can find these. So here is the row for 9 degrees of freedom. So I'm just going to highlight this row for you. Okay, so here is the row for 9 degrees of freedom. Then the alpha over 2 and 1 minus alpha over 2 values tell us the columns. So alpha over 2 was 0.05. So we're going to use this column here. So we're seeing the first value is 16.919. So I'm going to write it down here. Equals 16.919. Then the chi-square value with the subscripts of 0.95, so area of 0.95 to the right, is this one right here and this column. So I'm looking at this chi-square value, 3.325. So these chi-square values are giving us the chi-square value that has this area to its right. It's similar to the critical value z sub alpha over 2, except it lacks the symmetry. That's why we have to find two of them separately. Now we can go ahead and apply these to the formula. This confidence interval is for the population variance sigma squared, so I'll use that version of the formula. So the lower bound, it's in the numerator n minus 1, so 10 minus 1 times s squared was given, divided by the chi-square value found in the table. Can we get an approximation for that on the calculator? 10 minus 1 times 19.8 divided by 16.919. So I'm getting about 10.5. For the upper bound, it's exactly the same except that the denominator is different. This time the denominator is the chi-square sub 1 minus alpha over 2, which was 3.325. So put that in the calculator as well. Divide by 3.325. So I'm getting 53.6 approximately. So here is the confidence interval, 10.5 comma 53.6. Okay, so let's go ahead and write a little interpretation of that. We are 90% confident that the population variance is between 10.5 and 53.6. Okay, so part B, it's very similar. It's still a 90% confidence interval for the population variance, but this time the sample size is changing to 25. So let's make note of that. So if the sample size is 25, the degrees of freedom would be 25 minus 1, which is 24. So this will change the row we're looking at in the table. We have the same confidence level, so it won't change the columns. Alpha over 2 would still be 0.05, and 1 minus alpha over 2 would still be 0.95. So we're still finding two different chi-square values, this time with 24 degrees of freedom. So scroll up to the table. So here is the row for 24 degrees of freedom. So I'm going to highlight the row here. And the columns are the same, so let me bring this all the way down. Okay, so the chi-square sub 0.05, the chi-square with an area of 0.05 to the right would be 36.415. So write that down. And then chi-square sub 0.95 would be 13.848. Okay, so also keep in mind that when you use the formula, the numerator has n minus 1, n has changed to 25, so that will change that slightly as well. So the lower bound would be n minus 1, so 25 minus 1 times, the sample variance was still kept the same, 19.8, divided by chi-square sub 0.05, so 36.415. Get a approximation on the calculator, times 19.8 divided by 36.415. So I got about 13 point, it's like 0 if I round it to the nearest tenth. Okay, the upper bound, same exact thing except the denominator changes. We found that chi-square value to be 13.848. So let's put this in the calculator as well. Dividing by 13.848, 34.3. Okay, so you might notice that the S squared value, which is the sample, the point estimate, the sample statistic, is not in the center of these. That is because the distribution is not symmetric. Okay, so a similar interpretation. We are 90% confident that the population variance, we don't really have any more information than that. The population variance is between 13.0 and 34.3. So notice that these were both 90% confidence intervals. Part A, the sample size was 10. Part B, the sample size was 25. So Part C is asking us to compare. How does increasing the sample size affect the width of the interval? Well, you can see that this interval here, the second one we found, is actually a smaller interval. So the width of the interval has decreased, which makes sense, of course. The larger the sample size, the more accuracy we're going to have. So let's write that down as well. Larger sample size, more accuracy. And we've seen that over and over again in this chapter. Okay, let's take a look at an example that has more of a story to it. Investors not only desire a higher return on their money, but they'd also like the rate of return to be stable from year to year. Okay, stability is something that's measured using standard deviation. If the standard deviation is low, that shows stability. An investment manager invests with the goal of reducing volatility, which is year-to-year fluctuation in the rate of return. The following data represent the rate of return in percent for his mutual fund for the past 12 years. Part A, determine the sample, standard deviation, and sample variance. Okay, so let's go ahead and put these values into list 1, 13.8, 9.6, 15.9, 12.4, 10, 10.3, 12.4, 8.7, 11.3, 14.9, 6.6, 6.7. So I put these into list 1, and then we're going to do one variable stats. So you've done this many times, you might remember, it's stat calc number 1. List 1, there's no frequency list. Okay, so the sample standard deviation is S. S is about 2.979. Sample variance is not given in the calculator, but remember the variance is just S squared. So we can do 2.979 squared in our calculator, 2.979 squared, and that is about 8.874. The reason we found those is because we do need the sample variance in the formula for the lower bounds and upper bounds of our confidence interval. Construct a 95% confidence interval for the population standard deviation rate of return. So this time we're approximating sigma, which means we use the version of the formula that's inside of radicals or square roots. Before we apply the formulas, we do need to find our chi-square values. Since the confidence level is 95%, the alpha is 0.05. Remember, it is the complement. The complement of 95% is 5% and as a decimal. Alpha over 2 will be 0.05 divided by 2, which is 0.025. And 1 minus alpha over 2 is 1 minus 0.025, which is 0.975. So remember that these are used to find the columns in the table. To find the row, we need the sample size. Well, the sample size in this case was 12. So n equals 12, which means the degrees of freedom is 12 minus 1, which is 11. And that tells us the row to use. So we're going to find two chi-square values, chi-square sub 0.025 and chi-square sub 0.975. And those will both be found using 11 degrees of freedom. So let's go back up to the table. So I'm going to scroll up. 11 degrees of freedom is right here in the table. So this is the row we'll use. The first subscript was 0.025, which is right here. So my first chi-square value is 21.920. So let's write that down because I'm going to forget. 21.920. The second chi-square has a subscript of 0.975 or an area of 0.975 to its right. Let's go back to the table. That'll be right here. 3.816. So let's write that down. 3.816. Okay, now we have all the ingredients we need to apply the formulas. So the lower bound is the square root. This time I'm using the square root because we're finding a confidence interval for the standard deviation. N minus 1, so 12 minus 1 times s squared, which we found above to be 8.874, divided by the chi-square sub 0.025, 21.920. The most common mistake that students make is they forget to square root it. Remember that the formula without the square root is for the variance. The formula with the square root is for the standard deviation. So 12 minus 1 times 8.874 divided by 21.920. I got about 2.11. The upper bound is, the formula is identical except the denominator changes. So it's still the square root of 12 minus 1 times 8.874 divided by, this chi-square value is 3.816. Okay, so we'll type that in the calculator as well. So we're dividing by 3.816, and that is about 5.06. Okay, so the interval is 2.11 comma 5.06. So we are 95% confident that the population standard deviation rate of return, that's what we are estimating, the standard deviation of the rate of return is between 2.11% and 5.06%. Okay, so one more part C. The investment manager was not supposed to have a population standard deviation for the rate of return. Was not supposed to. I think that's a typo. I think it should say was supposed to. Sorry. The investment manager was supposed to have a population standard deviation for the rate of return below 6%. Does the confidence interval validate that desire? Well, if you take a look at the confidence interval, the entire thing lies below 6%. So does the confidence interval validate the desire? Yes. The entire interval is below 6%. Remember that they want it to be stable, so they want a low standard deviation.